acid, bases and salt. Already you are studied in lower classes what are acid, what are bases, what are salts. Just I will recall it. Acids are sour in taste, that is usually gastric juice secreted by the in lining of stomach, that is called HCl, hydrochloric acid. Then the fruit juices like citric fruits, orange, lime, they contain acid, that is an acetic acid like vinegar. These are called acids. And bases like bitter in taste, sodium hydroxide, calcium hydroxide, like this. Then salt, there is sodium chloride, potassium chloride. So these are the salts. Generally they have positive and negative charges, and they have a electrostatic forces attraction between them. For example, NaCl, if you take NaCl, so NaCl, Na plus and the Cl minus ion. So here the sodium having positive charge and the chloride ion having the negative charge. So they, in between the sodium and chloride ion, they have a electrostatic forces of attraction between there. So these are the basic concepts of acid, base, salts. Next is the Arrhenius concepts of acid and bases. So according to the Arrhenius theory, acids are substances that dissociate in water to give hydrogen ion, that is H plus aqueous, and the bases are substances that produce hydroxyl ion. See, look at this. The acid HX is aqueous solution to form that's to dissociate in H plus and X minus. So here X minus also in aqueous form. Or you can write it HX react with acid, that water to form hydronium ion and X minus aqueous. Either you can write H plus or H3O plus, both are indicates acid only. In a bare proton, here H plus is very reactive and cannot exist freely in aqueous solution. So thus it bonds to oxygen atom of a solvent water molecule to give trigonal pyramidal structure, that is the hydronium ion having trigonal pyramidal structure. That is the trigonal pyramidal hydronium ion, that is simply you can write it H2O plus. See, in this topic we are going to learn, that is we have to use the H plus or H3O plus aqueous, that is interchangeably to mean that the same, that is a hydrated proton. Similarly, a base molecule like MOH, ion is in the equation. Look at this. According to the equation, MOH aqueous to dissociate M aqueous and the OH aqueous. The M indicates metal. The hydroxyl, that is the OH ion, also exists in the hydrated form in the aqueous solution. Arrhenius concepts of acid and bases, however, suffer from the limitation of being applicable only to aqueous solution, and also does not account for the basicity of the substance like ammonia, which do not possess a hydroxyl group. That's NH3, there is no hydroxyl group. Okay, so this concept is called Arrhenius concepts of acid and bases. Bronsted, Lowry, acid and bases. Here Bronsted and Lowry, Danish and English chemists, they gave a more general definition of acid and bases. According to the Bronsted-Lowry theory, acid is a substance that is capable of donating a hydrogen ion, that is H plus, and bases are substance capable of accepting a hydroxide ion, that is H plus ion. In short, acid are proton donors and bases are proton acceptor. Look at this example. Here the NH3 react with acid. Here the NH3 is base and this is acid. See, the basic solution is formed due to the presence of the hydroxyl ion. Look at this. This converts to conjugate acid and the base. Here the adding of proton NH3 to NH4. Here look at this, losing of proton H2O forms OH. That means 2H, one hydrogen ion is lost. That is proton. One proton is lost to form OH aqueous. So this is called conjugate acid and conjugate base. That means the basic solution is formed due to the presence of hydroxyl ion, and in this reaction water molecule act as a proton donor and ammonia molecule act as a proton acceptor. So, and this is called Lowry's Bronsted acid and base theory. So, in the reverse reaction, look at this. In the reverse reaction, H plus is transferred from transfer from the ammonium ion to hydroxide ion. So in this case, the ammonium ion act as a Bronsted acid, while the OH act as a Bronsted base. So the acid base pair that differs only by one proton is called conjugate acid base pair. So therefore OH minus, that is hydroxyl ion, is called the conjugate acid, and the conjugate OH minus conjugate base, and the acid of H2O and NH4, that is NH4 plus ammonium ion, is called conjugate acid. That is conjugate acid of the base ammonia. If Bronsted acid is a strong acid, then its conjugate base is a weak base, and vice versa. So it may be noted that the conjugate acid has one extra proton. So conjugate has having this one extra proton, and each conjugate base has one less proton. Okay. Here look at another one example. HCl. HCl aqueous react with water to form hydronium ion aqueous and Cl minus aqueous. Here look at this example. In hydrochloric, that is the HCl, ionization of hydrochloric acid in water, HCl act as an acid. Here this is acid and this is base, and this is conjugate acid and this is conjugate base. Here the HCl act as an acid by donating a proton to H2O. So H2O molecule which act as a base. Then it can be seen that this equation, that water act as a base because it accepts proton. So look at this. This is adding of proton, and this is loss of proton. Water act as a base because of accepting proton. The species like hydronium ion is produced when water accepts a proton from HCl. So therefore Cl minus, look at this. This Cl minus is conjugate base of HCl, and HCl is the conjugate acid of base chloride ion. So similarly, water is a conjugate base of an acid in hydronium ion, and hydronium ion is a conjugate acid of base water molecule. So it is interesting to observe that the dual role of the water as an acid and bases. So in case of the reaction with HCl, water acts as a base, while in case of ammonia it acts as a acid. So by donating a proton, look at here water molecule act as a acid, here water molecule act as a base. So this concept is called a Bronsted-Lowry's acid and basic concept. Then Lewis acid bases. Lewis acid and bases. Here, this acid as a species which accepts electron pair and base which donates an electron pair. As far as bases are concerned, there is not much difference between the Bronsted, Lowry and Lewis concept. As the base provides a lone pair of electron, that is lone pair in the both cases. However, in Lewis concept, many acids do not have proton. For example, BF3 with NH3. So here the BF3 does not have any proton but still act as a acid and react with ammonia by accepting a lone pair of electron. That is BF3. The reaction is ammonia having the lone pair of electron, so to form BF3 NH3. So here the electron deficient species like AlCl3, CO3 plus, Mg2 plus. So these are the called can act as a Lewis acid, while species like H2O, NH3, OH minus, which can donate a pair of electron, so can act as a Lewis bases. So this is called a Lewis acid bases theory. Next is the ionization of acid and bases. Ionization of acid and bases, like Arrhenius concepts of acid and bases, become useful in case of ionization of acid and bases are mostly ionizations in chemicals and biological systems occur in aqueous medium. The strong acid like perchloric acid HClO4, hydrochloric acid, hydrobromic acid, sulfuric acid and nitric acid, like this. So they are called strong acid because they are almost completely dissociate in their constituent ions in the aqueous medium. That is why they are called strong acid. So thereby acting as a proton, that is a HCl, and HCl H plus act as a proton donor. Similarly, in strong base like lithium hydroxide, sodium hydroxide, potassium hydroxide, cesium hydroxide, so barium hydroxide. So these are called strong bases. These are almost completely dissociated into ions in the aqueous medium, giving the OH minus ion, that is hydroxide ion. According to the Arrhenius concept, they are strong acid and bases as they are able to completely dissociate and produce H3O plus hydronium ion and hydroxide ions in the medium. So alternatively, the strength of the acid or base may also be gauged in terms of Bronsted-Lowry concept of acid and bases, wherein a strong acid means a good proton donor and a strong base implies a good proton acceptor. See, look at this reaction example. HA is an acid. HA is an acid and H2O liquid is a base. So to form the hydronium ion H3O plus aqueous and A minus aqueous. So this is conjugate acid and this is conjugate base. Already we were seeing that is acid or base dissociation equilibrium is a dynamic involving a transfer of proton in the forward and the reverse direction. Now the question arises that if the equilibrium is a dynamic, then with the passage of the time, which direction is favored? What is the driving force behind it? So in order to answer these questions, we shall deal into the issue of the comparing of strength of two acid or bases involved in the dissociation equilibrium. See, look at this. two acid like this is Ha and hydronium ion. Two acid and bases, that is a hydronium ion, acid dissociation equilibrium, that is in this equation. We have to see which among them in the stronger proton donor, whichever exceed in its tendency of donating a proton over the others shall be termed as the stronger acid, and the equilibrium will shift in the direction of weaker acid. So say that as Ha is a stronger acid than H3O plus, and then solution will be mainly contains A minus and hydronium ions. So the equilibrium moves in the direction of formation of weak acid and the weak bases, because the stronger acid donates a proton to the stronger base. It follows that the stronger acid dissociate completely in water, the resulting base formed would be very weak. That is, strong acid have a weak, very weak conjugate bases. So strong acid like perchloric acid, sulfuric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, like this, hydrogen iodide. So like this, so they have a strong acid. So will give a conjugate base like ion ClO4 minus Cl Br minus, Cl minus, Br minus, I minus in Hi. Suppose involving Hi, it gives I minus. So NO3 minus, HSO4 minus, like this. So which are much weaker bases than water. So similarly, is a very strong base would give you a very weak conjugate acid. On the other hand, a weak acid says, that is Ha, is only partially dissociated in aqueous medium, and the solution mainly contain undissociated Ha molecules. That is, typical weak acids are nitrous acid HNO2 is weak acid, HNO2, hydrofluoric acid HF, acetic acid CH3, COOH, acetic acid. These are the weak acid. It should be noted that the weak acid have very strong conjugate bases. For example, in NH2 minus, O2 minus, H minus, a very good proton acceptor, and thus much stronger bases than water. So certain water soluble organic compound like phenolphthalein and bromothymol blue behave as a weak acid and exhibit different colors in their acid and conjugate base form. That is HIN. The IN indicates indicator. Okay, acid indicator react with water, that is to form hydronium ion, aqueous, and indicator IN, that is conjugate B, conjugate base. This is conjugate acid, and this is acid indicator color of A, indicator color A. This is color B. See, so such compounds are useful as indicator in acid-base titration and finding out the H plus ion concentration. Next, ionization constant of water and its ionic product. Here, some substances like waters are unique in their ability of acting both as an acid and bases. Already we were seen, that is, in the presence of acid, that is HA, it accepts a proton and act as a base while in the presence of base. So that is B minus simply. So B minus, it is act as an acid by donating a proton. In pure water, one water molecule donates proton and act as a acid, and another water molecule accepts a proton and act as a base at the same time. So look at here. Look this equation here. One water molecule act as a acid and one water molecule act as a base to gives conjugate acid and conjugate base, hydronium ion and the hydroxide ion. So this is conjugate acid and this is conjugate base. So this is the dissociation constant can be represented by K is equal to hydronium ion H3 concentration of H3O plus and concentration of OH minus. You can like water molecule. So that's simply concentration of the water molecule. The concentration of water is omitted from the denominator as water is a pure liquid and the concentration remains constant. That's why the H2O is incorporated with the equilibrium constant to give a new constant that is called Kw. This Kw called ionic product of water. So H plus and the OH minus. You can write this instead of this the H plus you can write it. So this is called ionic product of water. Then the concentration of H plus has been found founded experimentally, that is 1.0 into 10 power minus 7 molar at 298 Kelvin. So under the dissociation of water produce equal number of H plus ion and hydroxide ion. The concentrations of the hydroxide ion is, this is for H plus ion, and the concentration of the hydroxide ion is equal to concentration of H plus ion. So that's why 1.0 into 10 power minus 7 m, the value of Kw, that is ionic product of water at 298 Kelvin. So here the Kw, ionic product of water, H3O plus, concentration of H3O plus and concentration of OH minus is equal to 1 into 10 power minus 7 power square. So that into m square. So here 1 into 10 power minus 14 or m square. So the value of Kw, that is ionic product of water, temperature dependent and it's an equilibrium constant. So the density of the pure water is per 100,000 gram per liter and it's the molar mass will be what? 18 gram per mole. So they form the molarity of the pure water can be right like that is H2O, concentration of H2O is equal to 1000 gram per liter into 1 mole divided by 18 gram. So it will become 55.55 molar. So therefore the ratio of dissociated water to the undissociated water can be write like this, that is 10 power 7 divided by 55.55 is equal to 1.8 into 10 power minus 9, or you can write simply 2 in 10 power minus 9. So thus equilibrium lies mainly towards the undissociated of water. So we can distinguish that is acidic, neutral and basic aqueous solution by the relative values of hydroxide ion and hydronium ion concentration. For acidic, H3O plus is greater than OH minus. For basic, H3O plus is less than hydroxide ion. The neutral, H3O plus is equal to OH minus, concentration of OH minus. So these are the conclusion. Next is the pH scale. We will discuss next class. Thank you.